Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video, we are going to start taking the first steps in modeling our transmission tower in Autodesk Robot. Now, while I was preparing this lecture, I realized that there is a lot of stuff to be considered when modeling those towers. So I might model the tower in it of itself and talk about the loads in another video coupled with the design, because there are so many things you have to consider when you model the tower. I have started explaining what a transmission tower is and what the different considerations are in that. If you haven't seen this video, link is going to be above on the top right. With that being said, let's dive into it. So I want to model this tower, but of course I'm not going to take this tower one by one because I have so many more things I want to discuss here. So I'll just go to Robot. So to do that, I'll go to my frame 3D design, because 3D building design is nice, but I really don't need slabs and contours and stuff like that. Just go to my 3D frame design. Of course, you can design 3D trusses in 3D frames by releasing. So now we are in the 3D frame design. I just start my axis definition, and the first thing I would like to define is my Z definitions. Now you see, there is a lot of Z axes here, but truth to be said, I'm a fan of first of all defining the main Z axis points and then define the secondary Z axis points. And assume that it starts from here, and the Z is going to be 0, 18 meters, 22 meters, 26 meters, and 32.5 meters. My X is not for now 0, and my Y for now is 0. If I apply that, I see a little tower like this that has the X equals 0, the Y equals 0, and the Z equals multiple values. All right, fantastic. So now I want to start modeling this. Remember, this is I'm assuming now, and this is usually the case, that the base of the tower and all those XY planes are actually squares. So if I see 7,000 here, it will be 7,000 the depth too. Now I got a nice comment from our dear subscriber Nisapai, who suggested that based on his experience, some people take the tower base to be L over 4. Now if you try this here, L over 4 is actually 7 point something. So I think that our dear subscriber actually hit the nail on its top, because it's the same thing. I also mentioned previous video that I like to keep it at least as big as the tower line. Okay, so in the X I have negative 3.5 and positive 3.5, because 7 meters is actually split into negative and positive. I want it to be symmetric. I remove the 0, I apply that, and now I have the tower footprint in the X-axis. In the Y-axis is going to be the same, because I said that the tower footprint, or the tower XY plane, is going to be a square. So if I do this now, you can see that this is the case. Now there's a little trick that is being played here. You see, the tower is not just a perfect tower. The tower here is actually a tapering tower, meaning that at the first power line, the tower got actually smaller. And that's the case for almost all towers. I mean, look at this. This is a tower from wikipedia.org, and it's the same thing. It's tapering. So your tower is tapering, and you need to take this into account. And assume that the value of the final tower width is 1,500 millimeters. Now I'm going to stick to the distances here, which is 1,500. But if you want to have more details, people like to use between 20% and 25% of your base tower here and the top tower. And if you try calculate that, well, 1,500 over 7,200 is actually 20%, so it still works. But of course, this is just guidelines. It depends from country to country. It depends from project to project. Look at this. It seems to be also the case, because you're only seeing part of the tower. As a matter of fact, how we would design this is to have multiple alternatives and see which one weighs the least. That's what we would do. I'll use 1,500, so I'll just basically do that. 1,500 over 2, which is 1.5 over 2, which is going to be negative 0.75 and positive 0.75 in the X. Also negative 0.75 and positive 0.75 in the Y. If you apply that, you see some strange things here, but we want to model our stuff. Now during the modeling here, and that's the reason why I decided to split it into modeling only without loads, I will be giving a lot of practical details here and from the field details. You see, what we usually assume is that those chords are made out of one piece. I know it looks like a truss, and I know you would be inclined to basically model each and every one of those elements as one piece. But in reality, what ends up happening is that we use one full piece for those chords. Now, you could model it to be a one full piece, But please notice that due to practical limitations, you might not have pieces that are 18 meters long from factories. You might have to splice your piece. In other words, you are now forced to cut your piece, you are forced to cut your cord into two pieces, not because it's structurally relevant. No, you are cutting this cord into two pieces because it's practically relevant, meaning that you don't have, or maybe at least as far as I know, you will not easily find elements or find sections that are 18 meters long. So due to practical reasons, you might have to split it into multiple pieces at certain distances, or even just pieces. And this is also the case in reality. I mean, take a look at this. You can see here, once again, this is the Wikipedia article. You can see here that the tower has been split here, the cord has been split here into two pieces, but here it wasn't. Now, what's the reason why it was split? In my humble opinion, it's because of practical considerations. Because you cannot have a piece that is 130 meters long. So yes, I'm gonna split my piece here at least into two pieces. Furthermore, you are forced now. The splitting here is due to practical necessity. The splitting here is due to structural necessity, because you cannot simply bend an element. Like, this is gonna be a nightmare if you use a bent element, because any problem in calibration or any problem in lengths would cause drastic problems for the tower. So here you are forced to split your tower by necessity because the slope changes. So I think that I will be considering the following. I think I will be considering two pieces for this one piece here, and maybe one piece here. So that's my game plan now. So to implement this, well, the first thing is I'll just not split anything. So for now, I will start doing my simple bars or members, and I will start by doing those chords. Now, I didn't design anything, so for now I'll just use placeholder sections, and later on I will be filling those sections correctly. So for now, this is only a placeholder section. This is not the final section. Still, I mean, it's a placeholder section, but at least it should make sense. So I'll just use me an L-shaped section. And I'll choose me an L shape that is 10 inches by 10 inches. It's a huge shape, but I'm just telling you this is only a place, or 8 by 8, for example. This is only a placeholder section, and I will define me one section like this, and I'll define me another section, which is a smaller section, like this. And notice I'm using equal length legs. I'm defining two sections for reasons later I will explain. So for now, I'll take the bigger section and start drawing. So I will draw from here and go all the way until here. You can see that this is the correct point because Robot gives you the X and Y and Z projections of the point. So you keep an eye on below, and I think this is the correct point. If you click here, you have your first element. Now notice that the cross-section is wrongly rotated. It's not rotated correctly. That's not how we do our towers. The cross-section should be rotated. I like to keep an eye on everything. Like, you have to plan stuff. So actually, I have a little paper notebook beside me here, and I'm writing as I speak. Give me a second. I'm writing as I speak on my notebook that I should check out section gammas. And it's good to write it on your notebook beside you because it's easy to forget. And I mean, if you forget it, somebody will eventually pick it up, but it's not nice to forget it for a career standpoint. So once again, this is my second element, and this is my third element, and this is my fourth element. So now I have my tower, at least for the first piece. Now notice I didn't cut it anywhere, but I don't care for now for cutting. I will cut it later. Now the second piece is from here to here, I think. Let me just quickly check. Okay, so now the second piece is from here to here, but there is one important issue I need to address. The height here was given, the height of the power line or something, was given from the base of this little truss here, trusslet if I want to call it. So I will assume that this is 1 meter. In other words, I will not finish here, I will actually go 1 extra meter here. So, and this is why I usually don't prepare entirely my modeling. I prepare the general game plan, but not the entire modeling, because I want to be surprised by those issues, and I want to think and deal with them on situ, in front of you, without any script that is ready. Yes, I script my lecture, but I don't script my modeling. So I don't want the script to be like just showing you everything that works perfectly. I want you to see me while I'm really thinking, not just making as if I'm thinking. So I added a 1 meter up because I am planning something here, and you have this. You have this. I don't want to mess up. I think I messed up. So I will not video edit this. I'll just delete it. And I just got a little, like my mess up senses were tingling. So let me just check very quickly and be a little bit more careful now. From here to here, and this is correct. From here to here, and from here to here, here to here. Okay, perfect. Now this makes sense. And finally, everything will converge to one final point. Now the final point was not defined here, so I have to define it very quickly in my xy axis. So x equals 0, y equals 0 is the point of conversion. And believe it or not, it's not easy to actually design the connection there. The point of conversion connection is not easy to be designed, but because you have 4 elements running into each other at that point. But there is a way to do that, and I will talk about how we might do this in the design video. But for now, I need to focus because I want to somehow capture the correct position of the point. I think I did that. Did I do that? Yeah, makes sense. Okay, so the rest is easy because I have now a point. I can easily just connect those things like this. Notice once again, my sections have a very strange gamma angle here, like this. This is not what you see typically. Like, no, this is beyond ridiculous. So going on with this, let's change the gamma angles that we have here, because those angles should be pointing inside, or at least partially inside the structure. Those angles are not correct, so they need to be corrected. So how can I do that? Well, we need to start playing with the gamma angle. So if you go to geometry and go to properties, you have something called gamma angles. And we can change the gamma angles of those members just right now. So starting with this, we want this to rotate 90 degrees clockwise. So you can actually select, of course, anything you want here. Now, 90 degrees clockwise seems not to be here, so if you rotate 270, it should work. And it does. Okay, so this is good, this is good, this is bad. It needs to be rotated 90 degrees. Yes, that's the one I want. And this one should be rotated, okay, let's see, 180 degrees. So far, so good. Now, those are perfect. What about those things? Now, I want to rotate this somehow. Let's take a look. I think 180 would be good enough. Don't get me wrong. The connection here is actually challenging to fit, to have a connection between an incline and a vertical. I will talk about more details how we do this in the future. But what I'm trying to say is, you see that usually somehow the angle between the inclined or the section of the inclined bar and the section of the straight bar seem to be somehow okay, somehow compatible. So if I go full 180, you see this, and it seems that it doesn't work, because take a look how the connection looks like. This is very important to consider in the beginning of your modeling. Take a look. Connecting this is going to be a nightmare, but if you somehow rotate this a little bit, so at least the surface with the surface coincides, then it should be a smooth sailing from now on. So how can I do that? Well, let's put a value here. And this time, first of all, I'll put it to 0 to put it back to its original self. And now I want to think. I want to rotate this not 180, but 225 and see if this works or not. Click here, and yes, it works perfectly. And you can see now the connection between the inclined bar and the vertical bar is as smooth as possible. So it's possible to put a plate here, basically, or a gust plate or whatever. When I did 180 before, it was this. It's very hard to plate it. And this is an extremely important thing, not only for this project, but in engineering in general. You should always keep in mind what practical considerations are. Don't just blindly put sections. For this one, now, I don't know, let's see, it should rotate like 180. Maybe, is it doesn't work? Check. It works. Okay, fine. I just did a blind thing here. Actually, I think all of them work. I'm surprised. I'm that lucky, right? Okay, it seems, now please notice that this needs to be like tried, but it makes more sense now. I think those sections look good. Also, those sections having this shape makes it easy to connect the diagonals and all kinds of horizontal members, because you have a plate, a leg that you can gust plate into it. Whereas if you had the beginning like this, 0, where can you plate it? Like you want to make I mean, think about it. You want to make a horizontal member and you have an incline on it. So how can you connect a horizontal member to this? This doesn't make any sense. Maybe you need to like replay this multiple times to understand what I'm trying to say. Okay, let's rotate them all. and I think we are done. I think we've done a good job in modeling this. Of course, here there is all kinds of intersections here. Of course, in real life, you don't have those intersections. You chamfer the elements and connect them accordingly. So for now, I think I have done the gamma angles correctly. So now we're not finished. We did just one little thing of the structure. Now, I have a modus operandi where I like to keep basically checking the structure. So I just pin everything. As a matter of fact, I assume it's fixed because I want to stiffen my. Now, by the way, if you assume it's fixed, you're assuming that the foundation doesn't rotate. So I'll assume it's fixed for now, and then later I will talk about the foundation if need be. So I'll run the analysis now. It should be stable. Of course, if you run the analysis blindly, it will open a dead load for you, and, well, it applies it. And, well, let's take a look. Deflection shape seems odd. So let me just very quickly check out normalize the thing. That's really strange. I'm surprised that you have this deformation. Let me just quickly scale it down. Okay, no, it was just a matter of scale. Okay, fine. So everything seems to be fine. Of course, the deflection horizontally is large because there is nothing stiffening the structure in the horizontal direction. Okay, so how can we fix that? Well, of course, we need to start putting our diagonals and our verticals. Now, truth to be said, I personally dislike the drawing suggested here by JICA because you can see that that causes all kinds of practical problems. I mean, take a look. Now, always when you suggest something, always think of a practical point of view. How would you do that? Well, a worker and you would have a length for this bar, a different length for this bar, a different length for this bar, and not even two bars are the same. So, for example, the distance here is not the same as the distance here, is not the same as the distance here. So it's kind of counterintuitive because this would be a practical and on situ nightmare to do. Whereas those make sense because those have seemingly equalish distances. So what I'm trying to say is that this looks fancy and all, but in reality, I don't think that this is easy to be implemented. My little trick is to first of all assume an equidistant bracing, horizontal bracing. All right, so if you ask me how many horizontal bracings and cutting points I have here, and what is my suggestion to this, the answer is really, I don't know, to be honest, because it depends, and this is a really nice idea to think about. If you increase the number of elements here, well, you decrease the load per member, decreasing its weight, but you are increasing the number of members, increasing the total weight of the structure. So there is like a minimum point where you get the best possible weight, the best possible combination of having an adequate number of members and having the smallest weight. So in that case, I would, for example, have 3 towers and check out one tower where I, for example, break this into 6 pieces. Another tower, I break this into 7 pieces. Another tower, I break this into 5 pieces and design all of those towers. Of course, the software allows you to design it very quickly and compare the weights and decide. So that's my approach. For now, I will not do a trial error approach. I will just assume that I have seven spacings here, basically. So how do I do that? We will do that simply by selecting this stuff and going to geometry and or edit, going to edit, divide. And with divide, you can divide a thing or a member by parts or by distance if you want. But for now, I want to divide it by parts. You can also divide by a plane, but there is no need because if I divide by 7 parts, it's going to be a horizontal plane. So I said I'm going to divide this into 7 pieces. So there we go. That is my 7 now. Now I want to generate a node without the member edge division, meaning that I'm not going to split this into different members because I assume that this is one continuous member. And now I just realized, and I'm not going to video edit this. And the reason why I don't video edit stuff is because I wanted to see how, while you are taking decisions, you are keeping an eye on something else. You see, when you say division, you generate nodes without member edge division. But wait a minute, I said that I'm actually going to split my diagonals here into 2 pieces for practical reasons. So this is some kind of counterintuitive. So the first thing I should do before I split anything into 7 pieces is to split my bars into 2 pieces and enforce member division because I want to force this to be split into 2 pieces. So this is something I forgot about and realized while I'm modeling. I'm not going to video edit this because I wanted to see how somebody gets to a sudden realization that something is amiss. Because catching yourself making a mistake and rationalizing about how to avoid it is much better than me just taking a video and telling you here is how it's done. So if you execute this now, you can see that now there are nodes included, and now each of those members has been split into two pieces. I want to split it into two pieces, not because of structural stress reasons, but because of practical reasons. Now, truth to be said, I wanted to split those into 7 pieces, but because now I have 2, I cannot split to 7. I need to split to 3 and 3 because I want it to be homogeneous when we split. Because look, how can you split this to 7, this to 4, and this to 3? It doesn't work. It must be like it must be symmetric somehow. So you can split it into 3, 3 or 4, 4. I'm gonna opt for 3, 3. Once again, the number of splits is something that affects the design and should be further investigated by the engineer. So I have now 3, 3. Remember, we are going to generate nodes this time without the edge division. So we will not divide our edges. So if I click here, it gets divided. Click here, here, and here. Also, the lower elements like this. And now I think that I have divided my elements. You look, you select here, you see that yes, you have selected some of those nodes. See, from all those nodes, there are some nodes who split the beam into the bar into two pieces, and there are some nodes who don't split the bar into two pieces. Of course, we split the bar into two pieces because practical reasons. Now, of course, this becomes a long endurance test, and I will just basically select me a different section. I think this section was 8 by 8 by 1, so I select me a section 8 by 8 by half. So why do I use a different cross section? It is because later I will design this structure and I will be using all my tips and tricks about how to select stuff based on its cross section. So it stands to reason to plan this ahead and basically have two cross sections, although those two cross sections are dummy sections. And you can see that this is done as you can see in the drawing. It's just a 3D system. It seems that there are no horizontal bars, but the horizontal lines were just planes where those lines connect. Now, this is not a must. There is a gajillion ways of doing a transmission truss or lattice steel system. For example, this one incorporates horizontal members with a gust plate in each horizontal member. But of course, it depends on what you want to do. You can assume, and this is important to notice, you can assume that here you have a connection and a gust plate like this. And you can assume also that here you don't have a connection and you don't have a gust plate like this. Now, truth to be said, I'm not really sure if there is a connection here or not. I don't see a bolt, to be honest. But the idea still stands. If there is a connection, you have to take it into consideration. If there is no connection, then you can ignore it. Also, it seems that there are some arbitrary horizontal elements being pushed here. Actually, I don't really care about this because, once again, I'm here to show you the modeling and I'm discussing all kinds of alternatives for this model. So for now, I will stick with the this one because it seems to make more sense to me. So I'll just draw my horizontals and my bracings as follows. So this is my suggested shape now. Of course, feel free to dispute this and show me your own shapes. Everything is fine here. So here's my first one. Of course, I'm gonna just draw my shapes here like this. And you can see where this is going. This is gonna get video edited very quickly. So, and of course I need to brace this. So one here and one here. Now there can be an assumption where you have this as a gust plate, and you can also assume that this is not a gust plate. It depends on your assumption. Also, a different type of tower that you might see is not this, but something like this. This is a different type of tower where you have an element that connects to the center of this element. Now, in that case, you should make, in that case, please notice that in that case, you are assuming that this element is one piece. See, there is a lot of types of towers you can do. I will just stick to this because it seems to look cool. That's the only reason. Now, please notice that there is no perfect design for the tower. It's all an assumption, and you can do it yourself. Of course, I need to make sure that my sections are correct, which is going to be a nightmare in and of itself. So you can see where this is going. It's going to get video edited very quickly. Okay, so first of all, it took me far more than I want to admit. So after a grueling task, I was able to rotate all those diagonals, to draw the diagonals and rotate them. But there was one thing. You see, this doesn't seem right. Like this connection in real life is not easy to achieve. So if I rotate this, now this becomes feasible. You see, you can easily put a pin here, a bolt here, and finish the job. So you see, it's kind of annoying, but you have to take it into consideration. There is no escape for this. So I'll quickly do those horizontals to make sense of it, because it's very important. I think I messed up, right? Yeah, I think I messed up. This works. This is not correct. See, it becomes a nightmare. I'm trying my best to... Yeah, okay, now it works, right? Yes, it works. Okay, so good. You see, you are responsible for drawing the correct stuff, so it's very important that you keep your composure and try to draw something that makes sense. So let's quickly video edit this. Okay, so we finished the first part of the tower. It seems our tower is taking shape, but it's a good idea to just run the analysis, to dry run it and see if it's stable or not. Now, it seems to be stable, and if I open the deflection shape and basically normalize the deflection, I just go to deflections here or deformation and normalize it. You can see now, of course, the top doesn't count because it's not braced, but you can see that to some extent the structure is behaving okayish. It's behaving as I'm expecting it to be. Now the top, of course, goes all haywire because it's not braced. All right, so we reached a big point where we are gonna start modeling those carrier lines, the points which carry the electricity. So of course those are trusses, and those are two-dimensional trusses in 3D, meaning that you have a 2D truss with a 3D bracing. Now first of all, those elements are usually one piece. You can even see this if you check out what usually is happening. You see this is a 2D element, 2D truss. It is being stiffened below by some X-cross bracings. So okay, let's basically do that. Now to do that, very simply, I'm just gonna once again go to Robot and now start doing my magic. So first of all, the height of the truss here, I assumed it to be 1 meter, so I'll stick to that, which means that I have to define a new X. Yeah, you see, it seems to be a simple structure, but it isn't. It takes a lot of time and effort to do that. But well, at least you see it now, so if you're faced with this in the future, it should be a piece of cake. Okay, so with that being said, I have my little thing here. Now I need to draw my truss. Now the truss is drawn from the center here to the edge. So, well, let's do that. I'm gonna go to bar and start drawing that, and I'm gonna use the same section because I think that this project, I'm planning to have this for this project 2 sections only, not 3. If you want to have 3 sections for this, you can. Okay, fine, you win. Let me just put a 3rd section just in case, because you want to design 3 sections. So let's go to L shape, select any section. It's just a dummy section, for example, this 5 by 5 or something. Remember, this is just a dummy section. I will be changing this in the future. So I'll just basically click here and implement my my truss basically. So how can I do that? I'll just quickly have to disable the section so that I can see everything. Okay, so I click on beginning here and keep an eye on the projection downstairs. So you have this, that's my first element, and then you have here another element to here. And I'm gonna copy this, by the way, so this time I'm not gonna draw everything. And now you have some bracings and some disconnect cuts, so we're gonna split this into 3 pieces. So let's do that. I just go to edit. I just go to edit divide and split this into 3 pieces. I'm gonna split this into without division. I'm gonna split this into 3 pieces and this into 3 pieces. And now I'm gonna just make my truss. So of course you can assume any truss. I'm just gonna assume this little thing. So basically from here, 1 to here, 2, and continue, 3, 4, 5. That's my truss. Oh wow, look, it did perfectly. I was worried that I should start changing my orientations, but this time it worked fine. Okay, I'm happy now. Although, I'm a perfectionist, so I think that the upper chord should be flipped, in my opinion. So okay, let me flip that, because I mean, how will you connect this? This doesn't look right. Like, how will you connect this in real life? Doesn't look right. See, those are the things that I'm trying to teach you beside Autodesk Robot. Like, especially for the new engineers who are like still starting their careers, those advice is something I hope that will help them become better engineers. So I'm trying just my luck until it works. Taking a look, yes, it makes sense. Okay, now don't mind those little things. I mean, this is okay. We can easily chamfer it, but at least the connection should make sense. You can still go one step further if you want and rotate this. As a matter of fact, I will do this. So yeah, see, it wasn't actually as good as I thought. So I'm gonna rotate this 270, hoping that it works. Yes, and this 270. Yeah, but now this is perfect. Now this is something you can connect actually. This looks perfect. And the same thing here. I mean, this is, I know it's annoying for the modeler, but it actually will have an effect on the design of and modeling of your structure. Okay, so we have modeled one of our trusses. Of course, I'm gonna copy this now, and actually I might mirror it, because if I copy it, it will not work. I just copy it and then later I will mirror it. So I just go to edit, copy or move. So edit, copy or move. I'm gonna move it from here. Also, I just checked out there are two nodes here, so there's a problem in the connection here, which means that I should delete those members. So I just quickly video edit and fix this. How will I fix this? I will just delete and redraw. Okay, so now it works perfectly, and now I'm gonna mirror it twice and, well, modify it. So give me a second to. I will just mirror it in front of you and then video edit my rest of the section gamma angle treatment. So I'll go to edit, or vertical mirror, and I'm gonna mirror it around the XZ plane at 0. Of course, it doesn't work because I need to first of all select. So I didn't select my members, so let's select them. I want to mirror this stuff, and now I'll go to edit, vertical mirror, select XZ, and select this to be my mirror point. So it mirrored, fine. And now I'm gonna select. Okay, there is a problem with the mirroring that it created. No, it's okay. It's all good. It's all good. I'm just a little bit skeptical. So it's good to be skeptical, by the way. So I just take this. Oh, you know what? Let me just put those little verticals here and finish this before I mirror. You know what? I'll video edit everything because I don't want you to get bored. There is nothing new here to say. Okay, so another grueling 10 minutes later. I think I am okay-ish with this somehow. Let me just think. Yeah, I think it will. I think it works. I'm not really sure, but I think it works. Okay, so I can mirror this to the other side. Of course, mirroring this will cause them to be once again misaligned, so I have to gamma angle it, but just to quickly show you the mirror. So I need a vertical mirror now. This time it's YZ because we mirror around this plane. Location is here, so you get a mirrored structure as you saw here. And will it be ready? Of course not. I have to. Okay, did it work? Of course not. I have to manually change the gamma angles, right? So I'm just gonna video edit this again. Later I can copy, but for now I will just have to go through this pain. Okay, so another grueling task later, and I'm looking at the at the watch. I think I've been recording since 40 minutes or something. I think I will not be able to finish the entire modeling, by the way. I might have modeling 2, part 2, because I don't want to just wing it. I want to discuss everything. For example, how those are connected, how you can make sure that those are connected or not. So I think I should not rush it, but well, it's been fun, at least for the viewer. So, okay, fine. I finished this level, so I'm gonna go to the next level. Now, how can I go to the next level? Well, I need to know where the next level is. So let's take a look. Now going back to the grid, which is here, I want to see the grid, so I'll apply that. And now I see the grid. I have one of those, so I need to copy it to the upper level. So I'll copy this, and later I will comment about this. So first of all, I'll just close that. I'll copy this, and and that's a good thing about not changing the tower here. Otherwise, it would be a nightmare to model. So I'll basically go to edit, and copy without any dragging, and I'm gonna copy it to the next level. So it was here. So I just take, I think it's gonna be 4 meters, right? So if I go up, it should be 4 meters. I think. Paste. Yeah, I think we're doing okay here. Also, I should have copied it twice, right? So well, since I didn't copy it twice, if I say execute, will it work? Oh, it does. Okay, fine. So if I run the analysis now, I'm guessing there is some instabilities, but let's take a look. Isolated node, see, the problem starts. Okay, or no, there was no isolated node. Let me just check. Let's remove the node numbers. Okay, deflection shape. Yeah, it seems fine. Yes, it makes sense. It makes perfect sense that those just bulge out because this tower has very limited vertical stiffness, and vertical bending stiffness because you don't have any spacings. So it will bulge out, and you can see that you can easily like bend this to your will. But the good news are all the elements are connected correctly, so I think it makes sense. We still haven't done any blunders in modeling, which is a good thing, by the way, because I usually hate having blunders. It's always a good thing and good practice to keep running the analysis at every stage just to make sure that you're not missing anything. Okay, so now I think the last thing is going to be to add those bracings, and well, let's do it. So going on with this, I think the tower here is small enough to warrant a simpler design instead of this. I'm thinking, to be honest, like, let me tell you what I think. I think that if you basically draw this, let me show you. If you draw this from here, now I need to open the nodal numbers because I want to make sure I'm clicking correctly. To here, so that's one element, and well, here, second element. So I was thinking instead of doing this W-shaped system, you can just make a simple bracing. Now tell me in the comment section what you think about this. I think this would be much more sensible because the tower is now smaller. However, I want to keep the general shape of the tower, so I'll just do it by hand. So one, I'll just drag it. 2, 3, 4, 5. And you can see where this is going, right? I'm gonna once again spend like a lot of time actually, and then I'm gonna video edit this to present you the final result. So I think while I was doing my grueling process of video editing, I thought that I wanted to discuss how I can split this into two pieces. Now, you see here, I want to split this distance, this vertical distance. I want to split this into two pieces, but I cannot because if you click on the beam, on this element, sorry, you can see that this element is a full length, so there is no half to be split here. So how can you do that? Now, there is a command that does that for you. It's found in, I think, edit and something called cut by plane. So you can cut by plane, but of course, to cut by plane, you need to know what the height is that you want to cut at. So it's basically the middle point between axis 3 and axis 4 in the z-axis. So if you go to the z-axis, 3 is 19, 4 is 22, so the middle point is 20.5. So I want to cut at 20.5. So I go to geometry, edit, cut by plane. I'm gonna cut by a plane that is xy at a height of, the point is 22.5. No, it was 1.5, 20.5. And the objects I want to cut are those things. So I just select them like this and apply. And you can see that now my objects have been cut and I've created a new plane for work. Now this cut is not what I want to design as an element. So it might be a little bit strange, like why did you cut? Is there another way of doing this without cutting? And the answer is yes. Let me show you. And this is one option. Now we are back to one single element. Let me just run the analysis because I've done so many things. I might mess up, so no errors. Perfect. So now back to our point. We want to cut this into a certain distance. So if you go to geometry, divide, edit divide, you can actually plant a point at a distance. So let me first of all select this stuff. Now I want to go a distance away from 2, or between 2 and, not 2 and 4, I want between 3 and 4, so it was 20.5 here. Now, element 2 is at a height of 18. To 20.5 is 2.5 meters. So I select those things, and I want to cut at a distance, not cut, I want to add a point at a distance 2.5 meters. So I go here in a distance and say 2.5 meters, executing, hoping that everything works. So let's take a look. Yes. And you can see that we have your points. You can see the points there, and those are now the middle points where you can do your next plane. So once again, I'll go back to my video editing. All right, so it seems it took me far more time than I thought it would take me. I was actually planning to finish the entire modeling of the structure, but I think that it was far more demanding than I thought. And actually, this is where the money is. Like, being able to model a structure and take into consideration all those kind of practical things that you should take into consideration is what makes one engineer better than the other. This is what makes you special. So I hope that the viewers of my channel have learned a lot of things in terms of modeling, and I will continue the model next week. Unfortunately, as I told you, like, you might see a video that is around, like, I don't know, 50 minutes long. In reality, it took me around 2 hours to do this because of all the video editing that I've done. So yeah, I think it was a success. I just run the analysis very quickly to make one final check before I save this to continue it next time. Also, I'm thinking to upload this as an attachment to the video. I'll think about this. I think I will upload this just for you to see. So okay, deflection shape, yeah, I think it makes sense. Now you see this time the deflection, of course it's not normalized, but you can see deflections here are much better because there is no bulging in the column because you have stiffened it in the bending direction. All right, so I think that's everything I wanted to talk about. I mean, it looks really fantastic, and I hope that you enjoyed the video. Now, before I close off, stay tuned for the next week because we're going to talk about the rest of the modeling as in releasing and as in loads. Because once again, I want to reiterate that I thought I could finish the modeling in one video, but it turns out it's longer than I expected. So I'm gonna maybe finalize the modeling next video with loads and how to calculate them and all those kind of releases. And then maybe later I will basically design it and produce some meaningful reports. Anyway, I hope that you enjoyed the video and that you liked it. If you have liked the video, then, well, comment, share, like, subscribe, and the liking, especially subscribing because it increases the range of my channel. As per usual, this is the Civil Engineering Essentials channel, and we will catch you in the next video.